What's good, everybody? Thermochemistry is it studies the amount of heat in chemical and physical processes. And there are two vocabulary words that you gotta know. So heat is just the transfer of energy between a hotter object. Let's say this one's hotter. To a colder object. So it's just the transfer of energy from the hotter object to a colder object. So it's based on a difference of temperature. While temperature, I'm just saying temp, is just how hot or cold something is. Now, when you're studying thermochemistry, the first step is to define your system. So a system is just kind of the part of the universe what we're studying on. So for example, if we're kind of focusing on, let's say, just this Lego block on this table. Okay, so we have this table, and this is like a Lego block. If we're focusing on this Lego block right here, this becomes the system. Everything else is defined. So for example, this table, this would be defined as the surroundings. Now, there are three types of systems. So there is what's called an open system. So say that we have this pot of boiling water without a lid. Okay, so this is a pot of boiling water. An open system is when energy and matter can be exchanged between the surroundings and the system. So this pot of boiling water, the water is evaporating, right? Which means matter is being exchanged between the system and the surrounding. And in addition, energy is being transferred from the system to the surrounding. So because this pot of boiling water is very hot, if you have like a table that it's on, it will transfer energy to the table. So, sometimes when you go in the kitchen, someone's cooking, if they boiling water, the room, or even, the table it's on, this pot of boiling water is on, feels really hot because the heat is going from the system to the table. The heat is being exchanged. This is an open system. Open. Now we have a closed system. So say we got this bottle of water, okay? So we got this bottle of water. Now, this bottle of water with a cap on it, bottle of water with a cap on it. So this is when only energy can be exchanged between the surroundings and system. So if this, so let's say if surroundings is once again another table, maybe the table, if it's hotter, or, depending on the temperature, the water bottle might give the table energy, heat might be transferred from the table to the water bottle, but matter can't actually be exchanged because this water bottle has a lid on it. So unlike this pot of boiling water that has no lid, where matter can just escape, in this case, liquid water, it can't really escape because it has this lid on it. So this is a closed system. So only energy can be transferred. Finally, we have an isolated system. And this is when energy and matter cannot be exchanged. So if you have like a thermo, let me try to do my best drawing of that. Okay, so you got something like this. So if you have like something like a thermos where heat and matter cannot be exchanged, this is an isolated system. So just to be clear, system is the part of the universe we're focusing on. And there's three systems: open system, which is when matter and energy can be exchanged. a closed system where energy can only be exchanged, and an isolated system where none of that can exchange. No matter, no energy can be exchanged. Now, some vocabulary you gotta know for this. So you have endothermic and exothermic. Endothermic is when your system absorbs energy from the surroundings, while exothermic is when system releases energy from surroundings. So the system, when it absorbs energy, it gains heat. So you would say that your heat, which is denoted by a Q, your heat would increase. While endothermic, well, your heat would decrease. It's releasing energy. So endothermic, the heat for endothermic stuff, let's say like an endothermic reaction, it would be positive. But the Q for exothermic, because it's releasing energy, the heat or the Q would be negative. Now, let's say we're trying to go from a piece of ice to liquid water. Liquid water, okay. Would that be an endothermic or an exothermic process? Well, the ice has to gain energy. Let's say if we put this piece of like hot metal near it, the ice is gaining energy, and it's absorbing energy from the surroundings to melt into water. So this would be an endothermic process. I'm just write endo for short. And you see that when the arrows point kind of this way, these are all endothermic processes. Water to vapor. You have to boil the water. You have to give the water some heat. And then when the water absorbs the energy from the surroundings, it goes into a gas phase. So when you're melting ice into water, that is endothermic. When you're vaporizing water into gas or water vapor, that is an endothermic. And when you're sublimating ice into gas, that is also endothermic. All of these are endothermic. And if we were to go backwards, let's say vapor to water, well, the gas particles, these are the gas particles, they have to release their heat to go back to where they were, to go back to the liquid state. So this would be an exothermic process. And same with the water. Water to ice. The water, let's say we have this piece of water. The water has to give energy to its surroundings so that it becomes colder. It loses heat, and then it turns into ice. So this would also be exothermic. So gas to liquid or condensation, that would be exothermic. Water to ice or freezing, that would be exothermic. And deposition, gas to ice, that would also be exothermic. Now, another concept we're going to talk about is enthalpy. Enthalpy is the total heat content of the system, of your system. And you can express it as H equals the enthalpy of the system equals to the internal energy of the system plus the pressure of the surroundings, and this is going to be multiplied by the volume of your system. And enthalpy is really useful for, studying the change in your total heat content. Your change in enthalpy, you express it as like this. Your change in enthalpy during like chemical reactions or just natural processes like phase changes. And let's say that we have this pot and when it's under a stove, this pot is going to be our system. This is what we're going to be focusing on. If we kind of turn on the heat, the pot's enthalpy, you would say the heat content of the pot would increase. And if you turn off the heat, well, you can say the pot's enthalpy, it decreased. And when enthalpy increases, it has a positive sign, and when enthalpy decreases, this will have a negative sign. Let's talk about the first and second laws of thermodynamics. Energy cannot be created or destroyed. Seems pretty self-explanatory. If you have a light bulb here, you can't, and you're here, you can't just magically turn it on, without, a light switch or, some kind of energy source. If there was no energy source, you cannot just somehow turn a light bulb on. But energy can be, changed. So what I mean by that is, let's say if we have some solar panels, okay? And the sun's light energy hits it. This light energy will be converted into electrical energy. And electrical energy can be used to power up this light bulb. So energy can be converted into different forms, but you just can't randomly create or destroy energy. The second law of thermodynamics states that the amount of entropy in the universe is always increasing. And entropy just means the disorder of your system. Now, to kind of visualize the second law of thermodynamics, say we have a box full of gas particles. If these gas particles were to be clumped up in the corner, well, what happens after some time? After some time, you'll see that the gas particles, they're going to be more spread out from each other. Over time, the gas particles, they're just going to be messier and messier. It's more likely that you're going to see the gas particles arranged like this than arranged like this, where they're kind of compact, they're ordered in this one corner. And this is the same thing for the universe. Say that we have this boiling pot of boiling water. The heat is just naturally going to spread out, and everything is just going to be more disordered. And a common analogy that people use is that, your bedroom will naturally become messier and messier without you even noticing it. Over time, it's just going to be like that. If you drop a cup and it breaks, it's not just going to randomly, it's just not randomly going to go back to, and you drop it, it's not just going to be randomly going back to where it was without, actually using energy to do it. Over time, the glass will just become messier and messier. If you leave a fruit out on a table for too long, over time, it's just going to become messier. It's just going to start molding, So everything in the universe is just going to become messier, more disordered, and, there's more likely in the universe for something to be disordered than for it to actually for everything to be ordered, like, this gas particle example. Solids, well, you see these have kind of like an orderly structure, so they have the lowest entropy. Gases, like this, they have the highest entropy because, they can be arranged in so many different ways. Well, solids, well, you only see solids like this, but gases, well, you can see them like this, you can see them like this other arrangement. So gases have the highest entropy. And